Global data production is accelerating. By 2025, the International Data Corporation estimates the global datasphere will surpass 175 zettabytes. To physically hold that much information, we rely on massive, energy-intensive server farms spread across the globe. Our primary method for increasing storage density has been shrinking silicon lithography, but modern NAND flash memory cells are now only a few nanometers apart. We are hitting the hard limits of atomic physics. At this microscopic scale, electrons can spontaneously jump across insulating barriers. This electron tunneling and quantum interference degrades reliability, causing data corruption and making further miniaturization incredibly difficult. This chart illustrates the trajectory of storage density versus data growth. As data generation rises exponentially, the rate of density improvement in traditional media is slowing down, creating a severe and widening deficit. Even if we could manufacture enough drives, the media itself degrades. Magnetic tapes and hard disk drives suffer from mechanical wear and magnetic field decay, typically rendering them unreadable within 10 to 30 years. Maintaining this hardware also requires massive power. As detailed in the diagram, silicon microchips suffer from heat dissipation issues and high power consumption. Data centers must remain actively powered and cooled around the clock, even when information is rarely accessed. Fabricating high-density magnetic and solid-state storage relies on ultra-pure silicon, rare earth materials, and complex global supply chains that are vulnerable to disruption. Scaling our current infrastructure to meet future demand is physically and economically unviable. Surviving the data explosion requires migrating our archives off active electronic systems and onto a passive, high-density chemical substrate. Instead of engineering a new material from scratch, information theorists are adapting the molecule that preserves biological blueprints, DNA. Rather than relying on a binary system of zeros and ones, DNA uses a quaternary chemical system. Encoding data at the atomic level yields extreme volumetric efficiency. Theoretical models estimate that a single gram of synthesized DNA can hold up to 215 petabytes of digital information. In practical terms, the total global datasphere would occupy less than 1,000 kilograms of physical DNA. This massive storage potential was first demonstrated in 2012 by geneticist George Church and his research team at Harvard. Beyond density, molecular memory solves the degradation problem. Under appropriate cold, dry conditions, DNA remains stable for millennia. Scientists routinely sequence intact genetic information from fossilized mammoth remains that are tens of thousands of years old. Unlike optical discs or magnetic tapes, DNA provides inherent format universality. Because it is the fundamental operating system of biology, the tools to read it will always exist as long as humanity practices biotechnology. DNA offers a molecular framework to preserve human knowledge across timescales and physical densities that silicon cannot reach. Traditional computing writes information using variations in electronic charge or magnetic polarity, creating a binary string of zeros and ones. DNA storage swaps those physical states for molecular sequences using 4 chemical bases: adenine, thymine, cytosine, and guanine. To write a file, an algorithm groups binary source data into pairs, converting strings into base 4 format. Because 4 symbols are available, each physical unit carries double the information. The numbers 0, 1, 2, and 3 map to cytosine, adenine, thymine, and guanine. However, we cannot use a rigid one-to-one translation. Long, repetitive strings of a single base, known as homopolymers, frequently cause chemical synthesis engines to stall or induce reading errors during sequencing. The encoding algorithm must also restrict sequences heavily saturated with guanine and cytosine. High GC content causes the DNA strands to fold onto themselves, creating secondary structures like hairpins that prevent accurate data retrieval. To navigate these limitations, researchers apply advanced protocols like DNA fountain encoding or Reed-Solomon algorithms. These mathematically introduce redundancy and parity checks into the sequence, ensuring that the file remains intact even if localized damage occurs. Before the digital sequence is finalized, specialized indexing tags and metadata headers are appended to each data block. Millions of molecular strands will eventually mix together in a liquid droplet, making these tags necessary to correctly reassemble the file later. Translating digital files into biological code is an exercise in constraint management, balancing maximum information density against the biochemical realities of the molecules. Current microchips pack memory onto flat planes. DNA moves this into a three-dimensional architecture, packing immense data within a helix diameter of just 2 nanometers. Looking closely at the strand's architecture, the physical data is anchored to a rigid sugar-phosphate backbone. This covalent structure serves as the mechanical chassis, locking the encoded nucleotides into a stable linear arrangement. The two corresponding strands run in opposite directions, one from the 5' carbon end to the 3' end, and the other from 3' to 5'. This predictable directionality dictates exactly how laboratory enzymes attach to the sequence to copy or read the data. Once paired, the flat, aromatic nitrogenous bases stack tightly on top of one another. The overlapping electron fields from this stacking provide significant chemical stability, shielding the data from ambient thermal fluctuations. This diagram details how those bases interact. Adenine connects exclusively to thymine using 2 hydrogen bonds, while cytosine locks onto guanine using 3. This rigorous complementary pairing serves as physical built-in error checking. If a chemical anomaly flips a base, the opposite strand retains the correct geometric counterpart, allowing repair enzymes to locate and fix the corruption. The helical architecture serves as a mechanical chassis, shielding and stabilizing the information sequences embedded within the strand. Moving to a functional IT network requires an entirely new hardware pipeline, consisting of 4 stages: encoding, synthesis, storage, and retrieval. In the right phase, the digital sequences are passed to synthetic DNA printers. Using phosphoramidite chemistry or specialized polymerase enzymes, these machines physically assemble the nucleotides base by batch to POUD. Next is the store phase. To prevent water from breaking bonds, the DNA is freeze-dried and placed into airtight microvials. For ultra-long-term archiving, these microscopic strands can be embedded inside synthetic silica particles or glass, heavily insulating the data against ambient radiation and oxidative stress. When a user needs to retrieve a file, the read phase begins. Rather than scanning a physical disk sector, technicians target the specific molecular indexing tags of the requested file using polymerase chain reaction, or PCR. Here, we see the biological mechanism for replicating genetic sequences. By utilizing DNA polymerase, the system exponentially copies only the requested data strands, acting as a highly precise molecular amplifier. This amplification occurs inside a thermal cycler. The machine repeatedly cycles between high and low temperatures, allowing primers and enzymes to build fresh copies. Once enough copies are generated, the liquid sample is fed into a high-throughput sequencer. Technologies like nanopore sequencing measure changes in electrical current as the molecules pass through microscopic holes, translating the chemical bases back into raw digital data. Finally, decoding algorithms read the metadata headers, strip away the synthetic redundancy, and assemble the scattered bit strings perfectly into the original file. We have taken the exact enzymatic processes evolved to copy cellular genomes and engineered them to operate as a high-fidelity read-write server. This pivot from electronic charge to molecular identity enables us to store data without the constant energy requirements of traditional media. Currently, the time required to synthesize the strands and sequence them back limits this technology strictly to cold archival storage. It is not yet practical for rapid, daily file access. However, engineers are already prototyping automated architectures. Future data centers will replace physical server racks with microfluidic plumbing and robotic liquid handlers, quietly managing exabytes of data in a fraction of the physical space. And unlike previous generations of archival hardware, where magnetic tape readers or optical disk drives eventually disappear from the market, the genetic code is the foundational language of the biosphere. Our ability to decode it will only accelerate. This extreme density and durability opens immediate applications for preserving national historical archives, securing massive medical databases, and reliably storing data on deep space missions. DNA storage represents a collision between biotechnology and information theory. The molecule nature optimized to record biological history is now being formatted to record ours. By adopting this biological substrate, We are constructing a zero-energy digital archive with the capacity to securely preserve human knowledge long after the civilization that created it.